In this video, I'm going to cover, broadly speaking, two topics in polarimetry. The first one is sort of another classification system for enantiomers, and this will be the D and L system. And the second thing will be sort of how to actually measure how much of an enantiomer you have in a solution. So you perform some kind of reaction and you will end up with a mixture of your enantiomers. And as we'll see, mostly it'll be 50-50, but you can measure if you have an excess of one or the other. And so in polarimetry, and I'm only going to cover this at the level that you would see it in like a 200 level organic chemistry class. So if you want a little bit more background on the actual polarimetry, on sort of the properties of light that are actually being used, then this is a really good video that came out fairly recently by 3 Blue 1 Brown, where he actually talks about how these molecules are actually causing the polarized light to shift, to rotate, which is what we're actually measuring here. So that's a really good video. And I also have my own video on the subject of light polarization. So if you want to know a little bit more about light polarization, you can check that out. And I'll put these links in the description down below if you are interested in that. So in this video, I'm essentially just going to, just take it as a given that enantiomers do shift the polarized light, do cause a rotation on the polarized light, without really explaining how or why they do that. And so in polarimetry, you have a setup that's basically like this. So you have a light source here, and so a lot of times they use the D line of sodium. So that's a specific wavelength. So 589 nanometer wavelength of unpolarized light comes out. You put it through this polarizer here, and that will polarize it. So we go from this unpolarized light here to the polarized light right here. So it's polarized straight up and down. Then we have our sample here, and that light will pass through the sample, and based on the excess of one enantiomer or another, it will cause the polarization to rotate. So this has rotated in that direction. Well, as I'll discuss here in a minute, if you have a 50-50 mixture of your enantiomers, you get 0 degrees of rotation on the polarized light. But then you have some linear analyzer, and so then you will have some kind of detector here, so that will actually see how much the polarized light has rotated, which is the thing we want to measure. And so I said we use this D and L convention here, and so the D means dextrorotatory, and so these are compounds that rotate plane polarized light clockwise, and we have levorotatory, which are compounds that rotate plane polarized light counterclockwise. And so the dextrorotatory we call D, or a lot of times you see it as plus, where levorotatory is L, and a lot of times you see it as negative. And so if you have even looked into like supplements and stuff, you may have seen things like amino acids listed as like L whatever the amino acid is, and that's because all the amino acids that all life on Earth uses are levorotatory, and so that's what that L means. Is it's just telling you about the enantiomer that's actually present in it, and so that's what the L means. You may have seen that before. You might have seen this before, but you don't see it as often in things like nutrition and stuff. But all the sugars that life on the Earth uses are dextrorotatory, so you might have seen like D-glucose or things like that, and so that's what those letters are sort of referring to. All right, So a compound's specific rotation, which we put in these square brackets, this is an alpha in the square brackets, is the rotation found using a 1 gram per milliliter concentration in a 10 centimeter, or what you often see listed as 1 decimeter, and is calculated by this. So you do it in something that doesn't have 1 gram per milliliter and doesn't have 1 decimeter, and so then you can just divide it by whatever the path length and concentration was, and that will give you what the specific rotation would be if you did have the 1 gram per milliliter concentration and the 1 decimeter path length. Yeah, so C is the concentration and L is the path length of the cell. All right, so we can look at an example of this. So we can look at these enantiomers of 2-butanol, or you might see it written as butan 2-ol. So these are sort of two ways of writing it. I think this is the newer one, but it's very common to see it written this way as well. So those two names are interchangeable, but we have the R and the S version here. And so an enantiomer of 2-butanol is placed in a polarimeter, and the rotation is measured to be 4.05 degrees counterclockwise. So we're doing this on a solution that is 0.15 grams per milliliter, and we put it into a tube that is 2 decimeters for measurement. And so we perform this calculation here. We have our observed rotation, we have our concentration, and we have our path length. And so we see that this is negative 13.5 degrees here. And so this is what it is for a single enantiomer. So if you have a pure enantiomer here. And so you may notice I have this 25 here and this D here. You'll often see this listed this way. So the superscript 25 indicates the temperature in Celsius at which the measurement is made, because the temperature can affect, well, I mean, it's not that it can, it will affect the amount of rotation. And so you always want to have that listed there. So the subscript D is, as I said, we use the sodium D line, the 589 nanometers. So we put that there because the amount of rotation is going to change depending on the wavelength of light, which is why the standard is to use the sodium D line, which is 589 nanometer wavelength. All right, so it's also important to know that the R and S designation of a molecule does not correspond to the D or L designation. So something that has an R designation in the RS convention could be either D or L in this new convention. And so it is currently not possible to predict the D or L designation of a molecule. So if you just know the shape of the molecule, you can't predict whether it will be D or L. So this has to be determined with measurement. And I say it's currently not possible because I would argue that if we could, solve the Schrodinger equation for an entire molecule, then it would probably be possible to predict which way it's going to rotate plane polarized light. But since we don't have anything that can do that, then it is not actually possible to predict whether a molecule is going to be D or L. And so the takeaway here is R and S do not correspond to D and L, and we can't predict D and L. It has to be measured. All right, so when we have equal amounts of both enantiomers, so when it's 50-50, we call that a racemic mixture. And so, as I said before, this is what's called optically inactive. So the polarized light is not rotated in either direction. And so our observed rotation is alpha equals 0 degrees. And a reaction that uses optically inactive, so whenever you see this right here, what that's saying is that it's not going to rotate plane polarized light in either direction. That's what optically inactive means. So a reaction that uses optically inactive reactants and catalysts which is important because biology uses optically active catalysts. That's what enzymes are. But anyway, so if a reaction uses optically inactive reactants and catalysts, it cannot produce a product that is optically active. So optically inactive reactants will form optically inactive products. So any chiral product must be formed as a racemic mixture. And so uh, we can look at that here. So we have this right here. So we have this 2-butone here. So this is our carbon that has this carbonyl on it. The specific kind of carbonyl here is a ketone. And so that this carbon is sp2, which means it makes a plane. So it makes a flat plane from which this hydrogen here can approach from the top of the plane or from the bottom of the plane. And so when this hydrogen attaches here, these things will sort of bend upward. If instead this green one attaches here, these things will sort of bend downward. And so we get this. So this would be the R right here, where this carbon is now an R and this carbon is now an S. So up here we had these hydrogens coming in from the top of the plane. This one we had them coming in from the bottom. And so we end up with a racemic mixture of the R and S to butanol. And so this would be optically inactive. So these reactants here, this is optically inactive, and that's just optically inactive because there are no chiral centers. So none of the carbons on this 2-butone are actually chiral, and so that's optically inactive. Then these products are optically inactive because we will get 50% of that and we will get 50% of that, and so that makes it a racemic mixture, and so it's optically inactive. And so yeah, this is what I was mentioning earlier. So enzymes and receptors and things like that in biology are all going to be specific for a certain enantiomer. And so this example here shows this R epinephrine, which is the natural epinephrine. So it's R and it's in the RS convention, and that's negative in the negative positive / DL system. Then there's this S epinephrine here, which is not biologically active. So this calls this an enzyme. You might also be able to think of this like a receptor. So like the epinephrine receptor is not going to be able to bind with this S epinephrine, this particular enantiomer here. It can only bind with this one. And so yeah, like I said above, all biological amino acids are L and all biological sugars are D. And so there are some bacteria and things that use some of the opposite ones, so L sugars and D amino acids. In fact, my undergrad research was on antibiotic resistance in bacteria, and so bacterial cell walls use some D amino acids, but for the most part, and 100% for humans in particular, it's going to be these L amino acids in these D sugars here. So yeah, here's just a few more examples. So this is that carvone. We discussed this a little bit in the previous video, but what's interesting biologically about this is when we have the plus version, this has the scent of caraway seed, which I don't actually know what that smells like, but this will smell like caraway seed, where this one has a spearmint scent. And so those will bind to different olfactory receptors, and so this one will give the scent of caraway seed, where this one will give the scent of spearmint. So the S will give the spearmint scent. And just one more example. So this is ketamine, where if we use the R enantiomer here, it's hallucinogenic. With the S, it has an anesthetic effect. And so most of the time, these are given in a racemic mixture, like especially if you're going to be doing it recreationally, you're probably going to get a racemic mixture. And so that's why you get kind of that, the effect that ketamine gives you. But yeah, again, this is showing that biology interacts with these different enantiomers different, and therefore the fact that there are enantiomers is more important than just kind of an interesting curiosity. This has like real world effects. All right, so now we're going to get to kind of the other thing, which is looking at how we sort of measure the amount of an enantiomer in our solution. And so we will be talking about optical purity here and enantiomeric excess. So when a solution is somewhere between racemic and purely one enantiomer, so somewhere between 100% one, 0% the other, and 50% one, 50% the other, we want to measure the amount of each enantiomer. So we can do this using the optical purity, or OP, of the mixture, and it is the ratio of its rotation of the observed rotation to the pure enantiomer. So you take a measurement, you get it, you use that equation from before to get the specific rotation from your mixture that is not necessarily 100%, and then you do the ratio with the 100%, the pure enantiomer, and put it into this formula. So for instance, if we have mostly plus 2-butanol with a specific rotation of plus 9.72 degrees and compare it with a plus 13.5 degree rotation of pure plus enantiomer, we get this. So this percent here is our optical purity. That's not the percent of the plus enantiomer in solution. We have to do more calculations for that. This percent here is just the optical purity. And so that's kind of its own percent there, although it will be used in the calculation of the actual amount of the plus enantiomer in our solution. And so we also have this formula for enantiomeric excess here. And so we have the difference in D and L divided by the total right here. So we have the excess of one over the other over the entire mixture times 100%. And so if we're using this number up here, we put in D minus L equals 72%, and our D plus L equals 100%. And so our D minus L plus our D plus L will be 172%. This negative L and this positive L cancel each other out. So we get 2D equals 172%. We divide both sides by 2, and we get D equals 86%. And so that is actually the percent of the enantiomer. So our solution is 86% the plus enantiomer and 14% the negative enantiomer. And so that is using the optical purity and enantiomeric excess to calculate that. So optical purity, so if we know the observed rotation and the specific rotation of the pure enantiomer, we can predict the percent of enantiomeric excess. And so for the enantiomeric excess, if we know the concentrations of the two enantiomers, we can predict the rotation we will observe. So together we can get the actual percent of each enantiomer. So this is the one that we used above, where we took this 172 divided both sides by 2, and so we got the D here. And so then with the L, we can just take 100% minus that. So that's how I got 86%. So 100% minus 86% is 14%. All right, so we can look at another example here. So if we have a mixture containing 6 grams of the plus 2-butanol and 4 grams of the minus 2-butanol, then we can get the enantiomeric excess, or the optical purity, this way. So we have our 6 minus 4, then the 6 plus 4 in the denominator, and so we get 20% for our optical purity. So the specific rotation of the plus 2 butanol, or of the pure plus 2 butanol, remember, is the plus 13.5 degrees. And so the rotation of this mixture will be our optical purity equaling our mixture over the pure right here. And so if we just multiply both sides by the pure there, we get this, and so we plug in those numbers, and so we can predict what the rotation of our plane polarized light will be for our mixture here. And so that's how you can use these formulas to calculate those things. So yeah, that is what I wanted to talk about in this video. So the polarimetry, remember, is just, it gives us this other way of sort of classifying enantiomers using this D and L, or plus and minus system. But that system is not in perfect correspondence with the RS system. So if something is R, it could be either D or L. We can't predict the D or L character of it, and so that's something we actually have to measure. And then using those measurements of the rotation of plane polarized light, we can get the optical purity, and then from that we can actually find how much of our solution is one enantiomer over the other. And so yeah, that is the take-home message for this video. I hope you found it useful, and I will see you in the next one.